Okay, we're off to chapter 12, which obviously is second exam material. We got our first one coming up tomorrow, yes, on 1 through 4 and 10. So in chapter 12 here, we're going to talk about bonding. And we're going to talk about all types of bonding in this chapter. Ionic bonding, covalent bonding. We will also talk about how to draw Lewis structures, some molecular geometry, and polarity. So just open up with here again. Really, there's two types of bonds we're going to talk about in this chapter. And again, there's an ionic bond, which is always between a metal and a non-metal. And really, because of a lot of those sort of periodic trends that we talked about out of chapter 11 there at the end, when they do get together, as we talked about, basically metals have all of the trends that they pretty much are willing to give away their electrons. They're not looking to gain electrons. Non-metals, on their hand, have all those periodic trends where they want to kind of keep their electrons. They want other people's electrons. They want to gain electrons. So as we'll talk about in this chapter, what happens when we get basically both of those guys together, because they are sort of on opposite extremes of the periodic table, we do get a transfer of electrons from the metal to the non-metal. And that's really what's going to create, as we'll talk about, our cation, which again is our ion with a positive charge, and our anion from the non-metal, which is again created as it accepts those electrons along the way. One of the main things that you should sort of understand in terms of an ionic bond is there is no sharing of electrons in ionic bonds. So there is no sharing of electrons here, as we'll talk about. And it is this sort of opposite attraction that sort of holds those guys together. Now, when we get into the other type of bonding that we'll talk about here, which is really covalent bonding, that is typically between two nonmetals. And once again, based on those sort of periodic trends, and really where the nonmetals are located up there on the periodic table, they're all pretty much sitting in the same location in the periodic table. And that means that they all really do share very similar sort of periodic properties, like I mentioned a second ago. None of the nonmetals want to really lose electrons. They're more interested in keeping the ones they got and maybe gaining some more. So what happens, as we'll talk about in this case, is because of that, the best that could sort of happen is that they will just agree to maybe share electrons, because neither one of them wants to give away their electrons completely, and they both are looking to really hang on to all the electrons they can. And in a covalent bond, which makes it very different than a ionic bond, we do have sharing of electrons happening. And as we'll talk more about in this chapter, that sharing of electrons, thank you, may be equal or unequal sharing, but there is some aspect of sharing happening in a covalent bond. So again, that is the major sort of differences between those two. And as I mentioned, it's really based off a lot of those periodic trends we talked about last time there in chapter 11. At least that one section of 11 we talked about. So let's start with really how we sort of in chemistry express sort of bonding and stuff like that. And a lot of times we'll use what is sometimes referred to as Lewis dot symbols. They're sometimes just generically called electron dot symbols. So sometimes places and books will just generically call them electron dot symbols. And with a Lewis dot symbol, we basically can use these Lewis dot symbols to represent bonding, both types of bonding, as we'll talk about. You can use it to represent ionic bonding. You could also use it to represent covalent bonding. But one of the things that's important that we touched upon, I think, the other day as well, is when we look at an atom, there really are different types of electrons sort of there. There are really the core electrons, which, as we talked a little bit about there, when we're doing the periodic trends, those core electrons are the ones that are closest to the nucleus. They're held tightly because of their location. And there are valence electrons, which are the outermost electrons. They're a little higher in energy level. They're not as close to the nucleus. And when we talk about bonding, it is all about the valence electrons. So it is all about the valence electrons and bonding. They are the ones that are involved in bonding. And they really are the ones that we see in Lewis structures, Lewis dot symbols along the way. As we'll talk about in a second, basically a Lewis dot symbol is the symbol, and pretty much we use one dot to represent a valence electron. So one dot represents a valence electron. There's really kind of no super rule about how to do it, other than a lot of times people kind of just go clockwise, put one dot, and then kind of pair them up. The only rule really is no more usually than two dots on each side. So there's four sides to your symbol. Two dots on each side is 8 electrons, and 8 is a really important number in chemistry. It is, as we will talk about, and we touched upon a little bit, it is the noble gases there, which is group 8 on the periodic table. And that, again, is really the whole point of any type of bonding you talk about, is, again, for everybody to sort of achieve the same electron configuration as those noble gases. They're very, very stable, and it's a very stable sort of situation. Now, remember that you can write electron configuration out to figure out the number of valence electrons, which obviously you probably won't do at this point since we haven't hit that chapter yet. That's coming up later on. So again, the easier way to figure out the number of valence electrons is, again, it equals the group number, as we talked about. So the number of valence electrons equals the group number when you go to the periodic table. So everybody in group 1 has 1, everybody in 2 has 2, 3, 4, 5, 6, 7, and 8. They all have the same number of valence electrons as the group number. The one notable exception, as we also, I think, talked about when we were talking about the periodic trends, is helium. So helium, which is number 2 up there, again, is a member of group 8, but helium only has 2 total electrons, so it can't have 8. So it has only 2 valence electrons. But everybody else there, obviously, in group 8 will have 8, except for helium, which will only have 2. The good news is, again, as we talked about, we could do transition metals the same way, but you want to use the 1 through 18 number when you do transition metals for valence electrons. But really, the good news is you won't draw anything in terms of Lewis structures that involve transition metals, so you typically don't draw any type of structures involving those guys, so you're usually in a pretty good shape. So as I mentioned before, again, we use our symbol and one dot to represent each of the valence electrons as you go through there. So here is an example of some of our Lewis dot symbols for our representative elements. Again, you can see everybody here in group 1 has 1 valence electron, 2 valence electrons, 3, 4, and again, just following it through there, 5, 6, 7, and 8. Once again, helium only's got 2. This is also why, for example, another really important thing to remember is when we talk about bonding, 8 is a really important number. Everybody wants to get to 8. The one exception, and you really should lock it into your head, is hydrogen. Because if you look at hydrogen, it just needs to travel to helium, which is the noble gas that comes after it. And it only needs 2 to get there. Everybody else will need 8, but hydrogen should not have more than 2. Yes, sir. Also, it won't have zeros. Yeah, so it will, in an acid, become H plus. That is correct. So that's a really important thing to remember for bonding. Is definitely hydrogen should never, ever, ever, we'll do it a couple more times there, ever, ever have more than 2 electrons, yes, unless you would like an X over it. Everybody else pretty much wants to get to 8 in most cases. So let's talk a little about, again, those sort of general rules. As I mentioned before, we're going to talk about the 2 types of bonding, which is ionic compounds and covalent compounds. And once again, metal and non-metal for our ionic, And that also should be something that's sort of just a lock-in. You see a metal and a non-metal together, it should just go, that's an ionic compound. We're not sharing electrons. We're going to get some ions that are going to form, and we're going to get those transfer of electrons. So that again should really be sort of an automatic when you're thinking about bonding metal, non-metal, transfer electrons, ionic compound form. Just like that should be almost an ionic positive lock in there. An automatic for the second one is again when you see two nonmetals. So when you see two nonmetals coming together, that also should lock in for you that here we're going to have some type of sharing of electrons. And again, in this chapter, we'll talk about equal sharing, unequal sharing, how you determine that. But the overwhelming thing that happens always is, again, we're going to get sharing of electrons. So that is the major difference between sort of what's happening in each of those situations. And a lot of times, sometimes people have trouble recognizing, what situation is happening. So that's why it's important to understand, am I dealing with a metal and a non-metal? Am I dealing with two non-metals? Sort of what's happening in that situation. And that can lead you hopefully to sort of the correct sort of idea of what's happening with bonding. Now, as we talked about with some of those periodic trends, things with low ionization energies tend to form cations or positively charged electrons, or positively charged ions, and they become again positively charged because they lose electrons. So when they lose electrons, they now have more protons than electrons and become positively charged. Remember that ionization energy is the energy needed to remove an electron. So if you have very low ionization energy, it does not take a lot of convincing for that thing to lose electrons. If you have a really high ionization energy, then it's the opposite there. It takes a lot of convincing to try to get them to lose electrons. Things with high negative electron affinity tend to form anions. Remember, electron affinity is the energy change that occurs when somebody gains an electron. And if you have an affinity for something, you like it. And obviously, if you have high electron affinity, that usually means that you like to gain electrons. And those are things, again, are going to be our nonmetals that are going to form those anions. So general, basically kind of our metals there, group 1 and 2 is mainly when we talk about bonding, we basically deal with our group 1, group 2, group 3, aluminum type situations. Again, when we get into our non-metal region, our halogens, oxygen, those guys, we're going to get some type of negatively charged guys forming. So let's take a look at an example here of what's happening in this sort of bond here. So we have something that is lithium fluoride. And once again, lithium is group 1 on the periodic table. And that would mean that if I drew this Lewis dot symbol, lithium would have one little dot there. Now, fluoride, remember that is a negative ion. It has the IDE ending. We talked a little bit about that at the end of chapter 4. And that is group number 7. And it should have 7 valence electrons because of that. Now, if we write, for example, the electron configuration, which obviously we haven't done that chapter yet, but I'm going to write it up here and sort of explain it, and hopefully you'll get the idea there. It'll be 1s2, 2s1. Remember that these first numbers are the energy levels, and 1 is the lowest in energy, and then obviously as the numbers get larger, you're going higher in energy. So in the case of lithium, that 2s1, the s, by the way, is was known as the orbital where the electrons are hanging out. But this one on top here is this valence electron right there. So that is lithium's valence electron. And these would be, again, their core electrons in this case, not involved in bonding. The 2 electrons that are hanging out here are the core electrons. If we wrote sort of electron configuration for fluorine, 1s2, 2s2, 2p5 in this case. And again, first energy level, second energy level, second energy level. So there are 2 there and 5 there. These are the 7 valence electrons that we see represented here, obviously in this picture. And obviously down here is our core electrons here for fluorine. So again, what's going to happen in this situation is when we have our metal, which has very low ionization energy, we have our nonmetal there, which is like high ionization energy, high electronegativity, high electron affinity. Basically, the lithium is just going to go, no problem, go ahead, take my electron. And the fluorine is going to basically pick up the electron. So we are going to get a complete electron transfer in this case. And it's at that point when lithium loses that one electron, it now will have a charge and it will become positively charged. Again, it has one less electron than it started with. So now it's got 3 protons and only 2 electrons, and that gives it the +1 charge overall. Now, the fluorine, on the other hand, will basically pick up that electron right about there. And when it does, it now has 1 extra electron than it started with, and it will pick up that negative charge. Now, as you can see on the right-hand side, this is definitely going to be an ionic compound. And by the way, I knew that right off the bat because, once again, that is a metal. That is a nonmetal. And that's an ionic bond automatic happening here. And we're going to get this transfer of electrons occurring. And it's going to result in these charges. Now, when you draw these sort of Lewis dot symbols for something that's an ionic bond, like I just did here, you do need to include the charges. So that indicates that there is no electrons being shared here, that you formed ions. So you do have to include the charges. And typically speaking, most people will do something like I did up there, either put a bracket around one of them at minimum or both of them, just to indicate again that those electrons are not being shared when you do that. First off, any questions on that? So that's an ionic bond. And why is this so important? What is going on here, or ultimately what is happening? So ultimately what's going on in this situation is when lithium gives away its electron, it no longer will have this guy on the other side. And that means lithium goes from 3 electrons to 2 electrons. So this lithium with a +1 charge has an electron configuration of 2. And if you take a look at the periodic table, number 2 on the periodic table is our friend helium. Yeah. And by giving away its electron, not neon, but helium, it becomes the same electron configuration as helium, or sort of helium, with it kind of looks like an N because it wrote an N. Let's try that again. There you go. It becomes the same electron configuration as helium. This is helium's electron configuration as well. Now, when we look at fluorine, and if we take a look at fluorine to begin with, remember that basically the maximum number of electrons you could have around your symbol there is 8. It has 2, 4, 6, and 7 to begin with. And where it has room is right there in that orbital. It basically has room for 1 more electron, as you can see in the picture. And that would give it 8. And what ends up happening is, again, the fluorine now becomes fluoride and picks up 1s2, 2s2, 2p6. So it picks up that 1 electron right there in that what is known as an orbital. And again, if we count up the top numbers in what I just wrote there, it has 2, 4, and 6 is 10. So if you count up all these top numbers here, this is how many electrons F minus now has, and that is 10. And again, if you take a look at the periodic table, number 10 is our friend neon. I was a little ahead of myself there. Which again is also a noble gas. And this, for all intents purposes, is the whole point of bonding. Is for everybody to get the same electron configuration as a noble gas, because that is, again, a very, very stable situation. So lithium by losing an electron, is able to back up on the periodic table to the noble gas that comes right before it. And fluorine, by picking up the electron from lithium, is able to go forward on the periodic table and end up with the same electron configuration. This is going to create a very stable bond, and that attraction again here between the positive and negative charges, this once again is what is holding that together. No sharing of electrons, electrostatic attraction, positive, negative attraction. Any questions on that there? Now, this again creates that really stable situation, and that is so really the purpose of all this bonding here. Let's take a look at another example here. And once again, as I mentioned, that Li plus and F minus unit is held together by electrostatic attraction. Again, no sharing of electrons. It is just that positive and negative attraction to one another. Let's take a look at another example, and this is calcium oxide. So once again, when I take a look at this example, right off the bat, calcium is a metal. Oxide is oxygen, which is a nonmetal. So right there, that is our combination for an ionic compound basically to be formed. And you really don't need any other information other than that two things, metal and non-metal, come together. Once again, if we take a look at the periodic table, calcium there is group number 2, and calcium will have 2 valence electrons in this case. And if we wrote sort of calcium's electron configuration, it would be argon 4s2. And if we really wrote it out, it'd be like 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. Once again, all these numbers here, if you count up all those numbers up on top, that is 6, 8, and 10, 12, and 6 more is our argon's configuration at 18. And that is what this little box represents. The bracket means that we have argon's configuration. Number 4 here is the 4th energy level. That is the 2 valence electrons that is happening for calcium in this case. Now, when we take a look at oxygen, oxygen is group number 6, which again means it has 6 valence electrons, 2, 4, 5, and 6. And if we do a little electron configuration for it, 1s2, 2s2, we're at there, 2p4 in this case. And once again, on the 2nd energy level, right there's 2 and 4 is the 6 valence electrons that we actually see in oxygen in this case. Once again here, we're going to get our metal and non-metal coming together, those periodic trends and low ionization energy there for calcium, and oxygen's wanting of electrons is going to cause a transfer of electrons to occur here. And at this point, we will have an electron head out over to oxygen. And if I do that, for example, and you look at the periodic table, I basically lost 1 electron, which would move calcium just 1 spot back to the left, and that would end up at potassium. And potassium is not a noble gas, and that's not a very stable situation. So in this case, calcium will want to lose, and things typically want to lose all of their valence electrons to end up in that stable state. And this calcium will then dump its 2nd electron over there to the oxygen. The result of that is calcium lost not 1 but 2 electrons, and that is when it's going to become positively 2 charged. Again, positively charged means it's lost electrons. 2 is how many? Now, the oxygen, on the other hand, has picked up those 2 electrons to add to its 6, and that's going to now give oxygen 2 more electrons than it started with, and that's going to make oxygen now have a -2 charge in this case. And once again here, no sharing of electrons. It is the positive charge of the +2 attracted to the negative charge of the -2. And again, that is what's holding that unit together. It's actually a super strong attraction that actually holds those guys together. Very, very strong attraction. It is so strong, again, you could heat the heck out of something like that and it will not break apart into a gas or anything like that. Now, what happens in terms of our electrons? Well, calcium gets rid of its 2 valence electrons, whichever one you want to take it from. And that's going to leave really calcium with a +2 charge of 1s2, 2s2, 2p6, 3s2. And then once again, if you count up the top numbers, that is 18 electrons. Once again, if you take a peek at the periodic table, number 18 is argon. So here, by calcium losing not just 1 electron, which would actually only move it to potassium, by losing both of its valence electrons, now ends up with the same electron configuration as argon, and pretty stable situation. Now, the good news is oxygen right there actually has room to pick up those 2 electrons. So it could just pop those 2 electrons in that orbital, as we'll talk about when we get to chapter 11, and it will have no trouble doing so. And that's going to cause this electron configuration now for oxygen with a -2 charge to be 1s2, 2s2, 2p6. And once again, if you count up those top numbers, which are the electrons, 2, 2, and 6 is 10. That once again is neon's configuration. So once again here in this ionic compound, both calcium and oxygen are able to achieve the same electron configuration as a noble gas. And once again, that really is the whole point of bonding. And it's going to create this really, really stable bond. Any questions on that? Now, a really important question is, in this case, like we see here with calcium and oxygen, and like we saw with lithium and fluorine in the previous example, does, for example, calcium here, when it becomes positively 2 charged, does it actually become argon? It does not, right? Because as we talked about when we talked about protons, electrons, and neutrons, it is the protons that determine the element. So here we're just changing the electrons. So calcium, for example, still has 20 protons. So it is still calcium. It is calcium with a +2 charge. The difference is it has the same electron configuration as the noble gas. So it becomes the same in terms of its electrons like the noble gas. It does not become the noble gas. So it does not become argon, nor does oxygen become neon there, nor did lithium or fluorine become something else. They just end up with the exact same electron configuration as the noble gases. So things with the same electron configuration are what are known as being isoelectronic with each other. Isoelectronic are things that have the same electron configuration. So, for example, calcium with a +2 charge and argon are isoelectronic with each other. They have the exact same electron configuration. Lithium with a +1 charge and helium, also isoelectronic with each other. Oxygen with a -2 charge, fluorine with a -1 charge, and neon, they are all isoelectronic with each other. They all end up with the exact same electron configuration. But once again, they are all different elements because they have different numbers of protons. Any questions on that there? So what happens if we put together a couple of things that we just talked about? And let's say what happens if we take together calcium and our fluorine. So let's just say we want to put together our calcium, which again has its 2 valence electrons, And once again, that's argon 4s2. Those are, again, the 2 valence electrons. And we put it together with fluorine, which, again, is group number 7 and has 7 valence electrons and a 1s2, 2s2, 2p5. And once again, these are the 7 valence electrons in this case. So once again, in this situation, what's going to happen is our electrons are going to transfer from our metal to our nonmetal. So calcium is going to send an electron over. Now, we kind of run into a little situation at this point when this happens. The situation is actually with the fluorine on the right. It started with 7 electrons, or valence electrons, and I just gave it one more from calcium. Can that fluorine at this point take any more electrons? It cannot, because it could only have 8, right? So you just like max out that fluorine. So that's good for the fluorine on the right. Problematic for the calcium, because again, if you look at the periodic table, if calcium just loses 1 electron, it will only back up to potassium, and that's not where it wants to get to. It does want to get to a noble gas. So in this situation, to sort of fix it, we actually need not 1 fluorine, but we would need a second fluorine in this case. And that second fluorine will now have a spot for calcium basically to dump its second electron to in this case. Now, calcium was able to, in this situation, dump both electrons, 1 to each fluorine, and overall it lost 2 electrons, and that will get calcium to where it wants to be, which is this positive 2 charge that will now back it up to where it needs to go. Now, each of the individual fluorine atoms have gained just 1 electron. And I'll just circle it, for example. And because it only gained actually 1 electron, it becomes -1 charged. And the second fluorine also gained just 1 electron and becomes -1 charge. And now when we look at it, this calcium is able to get to argon's configuration by losing these 2 electrons. Each of the fluorines are able to put 1 electron into that orbital there, and that will give each of these fluorines, 1s2, 2s2, 2p6, once again, that is 10 electrons, or neon's configuration. They both will now be able to get to neon's configuration. Now, by doing this, all 3 of these guys have now hit noble gas configuration in a very stable situation. Perhaps you remember at the end of chapter 4, when we were talking about formulas for ionic compounds, what we said was whenever you take something that is positively charged and you put it together with something with a negative charge, the overall charge needs to equal 0, right? It's got to balance out to 0. The reason for that is actually this, is the bonding aspect of it. In this case, we need not 1, but 2 of these to get us to our proper formula of CaF2, because now calcium is noble gas configuration. This fluoride and this fluoride are both noble gas configuration, and everybody achieves noble gas configuration. That is also why we do not, when we put it together like this, end up with something like this, because this means calcium did not reach noble gas configuration, right? Because it would only be able to lose 1 electron. So that is really the reasoning behind, as we will see in chapter 5 a little bit more in depth, but also what we talked about in chapter 4 at the end. The reason behind why we need to get everybody to 0 when we put them together in the simplest way possible is it allows everybody in that ionic compound to achieve noble gas configuration and achieve this really stable electron configuration. Any questions on that there? Questions on ionic bonding. And again, as you can see, if you are drawing something that is ionic, they do need to have the charges actually on there to indicate that they are ions. All right, the next type of bonding we're going to now switch over and sort of talk about is covalent bonding. And once again, covalent bonding is between two nonmetals. So just like you can lock in metal, non-metal, I'm going to get myself an ionic compound. You could lock in that two nonmetals is going to result in some type of sharing of electrons, and a covalent bond is going to happen. So again, that's really why it's super important. And sometimes what people kind of don't do is just take a moment and sort of see what you're starting with. You know, do you have two nonmetals, a metal, non-metal? What's going on? And that sort of helps you sort of direct yourself. So Gilbert Lewis, hence Lewis structures, suggested the idea of chemical bond formation as sharing of electrons. And I think on your handout it's okay, but my stuff's all over the place, so I'll just redraw some of this here a little bit better. So if we take something like hydrogen, which only has one valence electron, because again, hydrogen only has one electron total, and that is a valence electron. And we put two hydrogens together. Now, in this particular case, because they are both hydrogen in this case, they definitely going to have the exact same periodic trends in terms of ionization energy, electronegativity, electron affinity. Neither one of these, because remember, even though hydrogen's hanging out technically over there on the left-hand side of the periodic table, hydrogen is actually a nonmetal, right? So what's going to happen in this situation is neither one of them is going to want to give away their electrons. So when we get two nonmetals together, the best, again, they could do is go, well, I'm not going to give mine away. You're not going to give yours away. Why don't we just share? And we sort of envision that both of these guys end up sort of sharing these electrons together. And we end up with a pair of electrons being shared by both atoms in this bond. And if you sort of look at the hydrogen on the left, those two electrons count for it. And if you take a peek at the hydrogen there on the right-hand side, or left-hand side, those two electrons also count for it as well. So they are being shared in this situation. And you could represent that like I did there with dots. You could also represent that with a line when we share electrons. One line represents two electrons, or a pair of electrons being shared. So as we'll talk about, one line is what is known as a single bond, and it represents basically a pair of electrons being shared. As we will see, two lines is a double bond, representing four total electrons, or two pairs of electrons being shared. And a three pack of lines there is a triple bond, representing six electrons total, or three pairs of electrons being shared in this case. Now, through sharing, what is happening is the exact same thing is happening in the ionic compound. When I look at the hydrogen on the left in my sharing situation, it's got itself two electrons. When I look at the hydrogen on the right, it also got itself two electrons by sharing. Again, if we take a peek up there at the periodic table, number 2 is helium. By sharing electrons in this case, not transferring like we see in ionic compounds, both of the hydrogens here have achieved noble gas configuration, and now they're really happy and stable, and we're going to get this sort of bond to occur, which is, again, a single bond in this case. Any questions on that there? So what is holding these electrons sort of in place? Well, remember that both of these atoms basically have a nucleus, right? So there's like a positive charge happening there. There's like a positive charge happening there. So the electrons which are negatively charged between the two are going to be attracted to the nucleus of the guy on the left, but also attracted to the guy on the right. And that's what's going to kind of lock those electrons into place between the two atoms and kind of hold that unit together. And this is what is known as a covalent bond between two nonmetals, where we have definitely sharing of electrons here. The ultimate goal doesn't matter here by sharing. The ultimate goal here is to get to the noble gas configuration. So as we saw there in an ionic compound that we just talked about, where we form ions, metals are able to achieve noble gas configuration by losing electrons and going backwards on the periodic table to the noble gas that comes before them. Nonmetals are able to accept electrons in an ionic compound or bond and go forward on the periodic table to the noble gas that comes after them. Here in covalent bonding, everybody's achieving that noble gas configuration through the sharing of electrons, which is going to push everybody over there towards group number 8. Any questions on that? So again, that attraction between the nucleuses and the negatively charged electrons is really what sort of holds that bond together. So if we take a look at fluorine or F2, once again, fluorine here is group number 7, so it will have 7 valence electrons. And if we have another one here, it will also have 7 valence electrons. Once again, obviously, they're both nonmetals, and they're exactly the same nonmetal. So again, no transfer of electrons going to happen here since they're both nonmetals. This is going to be a sharing of electrons situation here. And that's going to result in a covalent bond being formed in this case, which can be represented like so. And once again, those electrons in the middle will count for both fluorines in this case. So put a little circle around here. That's going to give this fluorine on the left 8 electrons. This fluorine on the right, also sharing those guys in the middle, will also have 8 electrons. Again, through sharing of electrons here, we're achieving noble gas configuration for everybody within that covalent bond, and again, going to create a very stable bond. By the way, just like on the other one, you can represent the bonding electrons there with a line, the ones that are being shared, and the other ones with dots. So you can also draw this like so as you go through there. Any questions on that there? Now, as we'll talk about, sometimes, to get everybody to sort of this noble gas configuration and a stable electron configuration may just require a single bond, may require a double bond, or may require a triple bond to sort of do that. And we'll talk about, when to do any of those. Now, when we do look at this picture, there are actually 2 different types of electrons that we see in a picture for covalent bonding. All of these electrons that are dots that are not making any type of bond, and you know that because there is no other symbol written on the other side of those dots other than the one is stuck with it. These ones that are not involved in bonding have a very creative name. They are known as non-bonding electrons because they are not involved in bonding. Or if you're old like me, I probably will say lone pairs. So people don't use lone pairs all that much these days. But if somebody says lone pairs are non-bonding electrons, they are the same thing. They're basically all the dots are electrons that are not involved in any type of bond formation. So that is all those guys I circled. These are our lone pairs. And obviously here in the middle, where we do have the sharing of electrons, and they make this bond, those electrons also have a special name. Again, a very creative special name, which is known as, since they make a bond, they are known as bonding electrons. So being able to recognize bonding electrons versus non-bonding electrons is also really important for something we'll talk about later on in this chapter, which is geometry and molecular geometry. Being able to identify, what you got there. Whenever you draw a Lewis structure, you should always show all those electrons. So you should always show lone pairs or non-bonding electrons as dots. They should always be drawn on your picture. And you should show bonding electrons. It is your call on the bonding electrons. If you want to use dots for those, that's perfectly fine. If you want to use lines, you could use that. I would say a majority of most people will use lines to represent bonding electrons, but it is not incorrect or wrong to use dots for those as well. So if you want to use dots, you can as well. So a Lewis structure, again, is a representation, as we saw there, of covalent bonding. where we could show electrons being shared with a line or a pair of dots. A thing to remember that when we do draw Lewis structures, we are only really showing and sort of drawing the valence electrons. Those are the only electrons that are involved in bonding. So something like fluorine, which has 7 valence electrons, remember it still has core electrons, so it does have 9 total electrons to start with. But again, they are not involved in bonding, so they're not pictured in the picture. So don't misunderstand that when you see the picture like fluorine, or the Lewis dot symbol of fluorine, or it has not 7 electrons, but those are just the valence electrons. Again, it still has those core electrons. We take a look at the Lewis structure for water. We see a similar thing developing. Once again, just like in our fluorine, we take a peek at our water. And if you use dots for everything here, you'll end up with a structure that looks like this. So our hydrogen on the left here will end up with 2 electrons through sharing. Our hydrogen on the right there will also end up with 2 electrons through sharing. And our oxygen actually sharing electrons with both hydrogens will end up with a magical number of 8 electrons there through sharing. And obviously with our fluorine, as we saw previously, by sharing electrons, ends up with 8 electrons there on the left and also on the right as well. Now, obviously here, as I mentioned a second ago, we see hydrogen only needing to get to helium, right? So 2 electrons, no more ever than 2 electrons, and oxygen here getting to 8. Obviously, those numbers are important sort of numbers when we're dealing with bonding. And let's officially talk about what those numbers sort of represent. And that is the octet rule. And the octet rule is the rule that we sort of follow when we're doing bonding or drawing structures. And the octet rule basically says that everybody will continue to make bonds until everybody's got 8 electrons around it. The exception obviously is, as I mentioned, hydrogen. Hydrogen only 2. That means hydrogen should never, ever, ever be in the middle of a structure. It basically should look like this hydrogen. One line to a hydrogen. That one line represents 2 electrons. Yeah, that's pretty much always what hydrogen should look like. Hydrogen should never have dots around it. Hydrogen should not be triple bonded with dots around it. I'm just saying this because people just like to load up hydrogen, just kind of keep on putting stuff on there. Again, if you don't want a big X, just should look like that basically. Again, should always be on the outside. If you try to put hydrogen in the middle of something, it's going to have too many electrons, right? So again, you want to keep that in mind as you're going through this and sort of drawing things. Only 2 for hydrogen. Everybody else will have 8. Especially in this class, everybody else will have 8. We'll talk about some exceptions to the octet rule a little bit later, but we will not run into any of those in this class. If you go to 1A, you will run into them, but here we will stick to the octet rule as what we'll obey. Now, as I mentioned before, that is the key to what we're trying to achieve here, which is 8 valence electrons for everybody but hydrogen. And as I mentioned, in some cases, all you need to do to sort of achieve that is a single bond. A single bond will take care of everybody in a covalent situation, and we'll get our 8 electron sharing. So once again here, as I mentioned a second ago, single bond can be represented with a single line, or again, a pair of electrons being shared. As you can see right there, the pair of electrons are the single line. Now, sometimes a single bond is not enough to get everybody to the octet rule in that stable situation. And sometimes it does require perhaps a double bond to be formed. In the case of CO2, as you can see down here, the carbon in the middle actually needs to double bond on both sides with the oxygen to give the carbon 8 electrons in the middle, and each of the oxygens will end up with 8 electrons by making a double bond on both sides in this case. Again, a double bond, 2 lines representing 4 total electrons, or 2 pairs of electrons. being shared in this case. So sometimes single bond's all you need. Sometimes you need a little extra help there, you need a little bit extra sharing, if you will, and a double bond is needed. And in some cases, a double bond is not enough, and you may actually need a triple bond to form. As we can see here, nitrogen's an example. Here it needs to actually form a triple bond, which again is 3 lines are 6 pairs of or 6 electrons or 3 electron pairs. And again, nitrogen on the right-hand side has 8 electrons through sharing. Nitrogen on the left-hand side has 8 electrons through sharing. Now, also a cautionary note that people always screw up on when we get into drawing Lewis structures for covalent bonding. Everybody wants to like double bond and triple bond right out of the box, yeah? And that's usually not the best situation. You kind of want to only make single bonds. And then if somebody, as we'll talk about, doesn't really get to the octet rule, you then want to try to fix it by making a double bond. And if that should not work, then you kind of gotta go to triple bond. So best rule of thumb when you're drawing Lewis structures, we'll talk about a little bit later on here in this chapter, is you want to kind of single bond it, and that doesn't fix everybody, then go to your double bond option. If that doesn't fix it, then you want to go to your triple bond option. Once again, you just don't want a double bond right out of the box. Once again, here, triple bond between the 2 carbons and sharing electrons with the hydrogens gives each carbon 8. And if we look at each hydrogen still has only 2 electrons in this situation, which is exactly what it should have. Any questions on that there? All right, let's talk a little bit about electronegativity. As we talked about with periodic trends, we're going to talk a lot more about it, obviously, in this chapter. Electronegativity, again, is the ability of an atom to bring electrons toward itself. And remember, as we talked about, as we'll see here in a second again, as you go up and to the right, it will increase on the periodic table, and it will decrease as you go down and to the left. Fluorine is the most electronegative element you could have. So fluorine is the most electronegative. And we really use electronegativity in a couple places, but one of the main sort of things that we sort of use electronegativity to help us understand is when I have things that are going to share electrons, will they actually share these electrons sort of equally, or will they share them unequally? And really, electronegativity is the biggest thing that you want to look at to determine whether or not these electrons are going to be shared, like I said, equal or unequally. So for example, if we take our hydrogen bond that we saw earlier between our 2 hydrogens, and again, by sharing electrons there between our 2 hydrogens, 2 electrons, 2 electrons. Now, in this particular case, because both of these are hydrogen, they both will have the exact same electronegativity. And what that means is they are both, if you want to think about like pulling a rope, they're both going to pull the rope pretty equally, right? Exactly the same, because they're pretty much the same thing on both sides. And what that's going to do, if you just think of like a tug of war situation, if you have a rope and people are pulling equally on both sides, nobody's going anywhere basically, right? They were just kind of stalemated right there. And in this case, because of that, we would expect the electrons to be shared really equally, because they're both going to pull those electrons equally to each other. And if this kind of smeary thing I'm making here is the electron density, we would kind of expect the electrons to be kind of spread out relatively equally over the bond. And when we have this situation occur, this actually creates a certain type of covalent bond, and this is what is referred to as a nonpolar covalent bond. I would say pretty much everybody kind of leaves the covalent part out and just calls it a nonpolar bond. And that is where you have a situation like this where you're going to end up with equal sharing of electrons. So with equal sharing of electrons, you will create this nonpolar covalent bond. Now, one of the effects of a nonpolar covalent bond is because it is being shared equally, there is no charge that develops. So because the electrons are shared equally, they're really sort of spread out equally over the bond. It is kind of like a neutral bond. You can think of it as being like a neutral bond. There's like no positive side to it. There's no negative side. Everybody's all nicely sort of sharing those electrons. And we're not going to create any type of charges that are occurring. And that is a little bit different than if we swapped out one of those hydrogens for fluorine. And let's just say we put fluorine involved here, right? Now what we end up getting in this situation is electrons being shared between hydrogen and our fluorine. Again, giving fluorine our 8 electrons, giving our hydrogen our 2 electrons in this case. But now we have a very different electronegativity situation. As I just mentioned a second ago, the most electronegative atom in this situation is fluorine, is the most electronegative atom. And what's going to happen in this situation is those electrons are no longer going to be shared equally because fluorine, if you want to go back to the tug of war example of the rope, fluorine is going to pull that rope way harder than hydrogen is going to be able to hang on. And it's going to like move everybody towards fluorine. And what's going to happen in this case, because fluorine is more electronegative, which means it likes to bring electrons towards itself, what we're going to end up getting in terms of our sort of electron density is, instead of it all being equal, we're going to get like a lot more electron density happening on the fluorine side of the bond rather than the hydrogen side of the bond. And we're going to get unequal sharing of electrons here. And this unequal sharing of electrons is known as a different type of covalent bond. This is known as a polar covalent bond, or just a polar bond. So a polar bond results when you get two atoms that have differences in their electronegativity, and one of them will kind of bring the electrons closer to itself because it is more electronegative than the other. The electrons will always transfer or go near, not really transfer, but go closer to the atom that is more electronegative. It's going to kind of pull those electrons towards it. The result of this is also that because the electrons are now hanging out over on the fluorine side now becomes more negative because the electrons are hanging out over there. And the hydrogen side becomes more positive because the negatively charged electrons are moving away from the hydrogen. And it creates a partially negative charge on the fluorine. That's a delta symbol, delta negative, and a partially positive charge on the hydrogen. And it could also be represented, which was a arrow, which is known as a dipole arrow, where the arrow points to the more electronegative side, or negative side. And the part back here that kind of makes a plus sign is to the least electronegative side. Just the more positive side. And this is what is called a polar bond, and that is two nonmetals unequally sharing electrons. Why is these partially positive charges and partially negative charges, and why are they not full positive charges and full negative charges? Yeah. So why is it partially positive and partially negative and not fully positive and fully negative? Yeah. So what's really happening here is, again, they are still sharing the electrons, right? There's some aspect of sharing happening in this situation. And that is different than what we see in the ionic bond, where the electrons are not being shared, they're being completely transferred. And that creates a positively charged ion, cation, and a negatively charged anion through the complete transfer of electrons. Here in a polar covalent bond, they are sharing an electron still, and in this case, hydrogen's barely hanging on, but it's still hanging on to those electrons. So again, if you go back to sort of the tug of war with the rope, hydrogen's getting dragged across the dirt and hanging on to the rope, but he's still hanging on, right? And they're still sharing those electrons. And he hasn't decided to let go and just let it go. He's still going to hang on to it. And that is the difference here in a polar covalent bond and why we get charges that are partially positive and partially negative, because again, there's still aspects of sharing happening rather than an ionic compound or ionic bond where there's no sharing, just a complete transfer of electrons. Okay, we're going to continue on. So we're talking about sort of two different types of covalent bonds. Again, we have nonpolar bonds or nonpolar covalent bonds, which is a result of equal sharing of electrons between the two atoms within the bond. As I mentioned a second ago, it basically creates a neutral bond. There is no sort of positive side or negative side to that bond. What we finished up on there as we were just before our break is polar bond or a polar covalent bond. That is a situation where we do have two atoms within a bond that does have some differences in their electronegativity values. And one is going to be perhaps more electronegative than the other. And the result of that is the one that is more electronegative is going to sort of really attract the electrons closer to itself and kind of away from the other atom within the bond. The result of that is because the electrons are now moving closer to the more electronegative atom, it's going to create the side of that bond where the more electronegative atom is to be more negative or partially negative. And the side where the electrons are sort of moving away from is going to now become partially positive again, sort of that unequal sharing of electrons, creating these really charged type of bond where one side of the bond is more positively charged and one side is more negatively charged. And again, as I mentioned, that is what we do see when we do swap out, again, perhaps one of the fluorines for a hydrogen and we get HF. Again, because fluorine is the most electronegative atom, definitely going to drag those electrons closer to itself. As we also talked about, again, the reason we get partially positive and partially negative bonds here and not like full positives and full negative charges is there is still some aspect of sharing happening here. So the hydrogen, for example, in this case, is not just like, go ahead and take my electrons, still going to try to hang on to it a little bit. And there is some aspect of sharing that's going on. As I also mentioned, you can basically represent this one of two ways. Again, this is what is sometimes referred to as a dipole arrow. And again, it always points to the more negative side of the bond. Really, the more electronegative atom is where it points to. In the back end, as I mentioned earlier, where it kind of makes almost like a plus sign, should always be on the side that's the least electronegative. And that's going to be the more positive side of that bond, is where you find that. So you could think of really the three types of bonding that we talked about to this point as, sort of extremes. On the one extreme, you have an ionic bond. And again, that is always between a metal and a nonmetal. And we're always going to get a transfer of electrons from the metal to the non-metal in this case. And as we talked about earlier, that is what's going to get you your cation from the metal that's positively charged, your anion from the non-metal that's negatively charged. And it is, again, no sharing of electrons here. It is just the opposite attraction, electrostatic attraction. And an example of that would be something like sodium chloride. On sort of the other end of the extreme, we have a nonpolar covalent bond, or just a nonpolar bond. And that is going to be between two nonmetals, where basically we're going to definitely share electrons here, and they're going to be shared equally. Once again, creating a really even distribution of electrons across the bond, and really no negative side, no positive side to that bond, really more like a neutral bond. An example of that is you could take your pick of a couple that we've seen, H2 or F2. Again, going to have those kind of equal sharing of electrons. And then sort of in the middle of these two sort of extremes, if you will, we have our polar covalent bond, or just our polar bond, also between two nonmetals. The difference here is we're going to have unequal sharing of electrons. And the result of that, as we talked about and can see here, is it is going to create that partially positive side and partially negative side to this bond because of the difference in electronegativity. And obviously here, HF that we've been talking about is definitely an example of that. So on one end of the extreme, ionic end of the extreme, you have no sharing, just a complete transfer of electrons. And that always happens with our metals and nonmetals. On the other end, we have a nonpolar covalent bond between two nonmetals is going to share the electrons perfectly equal and going to create that nonpolar bond. And in the middle, we have two nonmetals going to share the electrons unequally, not so unequal that they get transferred like we see in ionic bonds, but definitely not equal like we see in a nonpolar bond. Some degree of unequal sharing happening, again, in a case where the electrons would be closer to that more electronegative atom. Any questions on the differences there? Now, as I mentioned before, when we really talk about sort of, is this bond polar? Is this bond nonpolar? To some extent, you could use it for ionic bonds, but you don't really need the ionic bond and sort of electronegativity to help you decide that. Really, all you need for an ionic bond is I got a metal and a non-metal, and that's pretty much good enough in most cases. But really, where we kind of use electronegativity, which is again that ability of an atom to attract electrons towards itself, we use it a lot to help us decide how the electrons are going to be shared. Are they going to be shared equally? Are they going to be shared unequally? And electronegativity is based on electron affinity and ionization energy, those trends that we talked about in the previous chapter, or that little part of the previous chapter. Fluorine, which has a high electron affinity and a high ionization energy, is pretty much going to have a high electronegativity. A little extra O in there. And sodium, with a low electron affinity and a low ionization energy, will also have a low electronegativity. Now, how do we know? Whoops, come back. How do we know how those electrons are going to be shared? We talked about the general trend in electronegativity, which once again increases as you go up and to the right on the periodic table, with fluorine being the most electronegative element you could have, and decreasing in terms of electronegativity as you go left and down on the periodic table. A guy by the name of Pauling came up with a method of sort of calculating differences in electronegativity values. And on the Pauling scale of electronegativity values, the Pauling scale runs from 0 to 4, 4 being the most electronegative, 0 being not so much. So if you're at 4, like fluorine, for example, it is the most electronegative, and 0, not so much electronegativity. You're not really looking to bring electrons towards yourself. Now, we could use Pauling scale, as we will see here in a second, to help us decide what type of bond we would expect to occur. And we could do that by taking what is sometimes referred to as the delta En, and that is the change in electronegativity value. So the change in electronegativity value So how do you do that? Well, you basically use Pauling scale and you find the two elements that are within the bond, are making that bond, and you basically find their electronegativity values and you just subtract them. So you subtract the two values. Typically, you subtract them with larger number from smaller, so you get a positive number. Basically, just looking for the difference, really, not really negative or positive. So we're just going to subtract the two numbers. And if you do that and you end up with a difference in electronegativity of anywhere from 0 to like 0.4, that's going to be considered a nonpolar bond. And that's going to be a nonpolar covalent bond. If you do the difference in electronegativity and you're above 0.4, we'll call it 0.5 and above, and you're below 2, that's going to be some type of polar covalent bond, unequal sharing of electrons. And typically, if you are above 2, but not in all cases, you should have an ionic bond sort of happening in this case. Once again, personally, I wouldn't even worry about electronegativity for ionic bonding. Again, metal, non-metal, you're good to go in pretty much all cases. I would really focus more in on electronegativity values for sort of, is it a polar covalent bond, equal sharing of or non-equal sharing electrons, or is it a non-polar covalent bond, equal sharing of electrons? And I would kind of use it for that. The reason also ionic is not the greatest is that number. There are definitely values and compounds where if you take the difference in electronegativity, you'll get less than 2. There's like a 1.8, 1.6, so you get some variance that happens with ionic. So best for ionic, just go metal, non-metal, that's what it is, and use the electronegativity values really for the covalent bonding stuff and application. Here is a Pauling table of electronegativity values. And as you can see, as you go up and to the right on the periodic table, you can see up there, upper right corner, fluorine is 4, which is the most electronegative. As you hang there to the left and down, you got like 0.7, which obviously is closer to 0, not so electronegative. Why do we not go all the way to the noble gases? Because they are stable. They ain't looking to do anything, right? That's what everybody else is trying to do, right? Is to get like them. So they're not really looking to do anything. Typically, if you ever need a value for noble gases, usually most people use 0 for them, and they have really not looking to do much in terms of that. So if we take our examples just to show you sort of how this works, if we took our sodium chloride example, and we had HF, right? And we also had, we'll do F2. Why not? All right, so we got these guys. So for example, if we went to our table, we would find the value for sodium, which is 0.9. And we'd find the value for chlorine, which is there to the right there. It looks like 3, I think. And again, we could calculate the difference in electronegativity by really just subtracting those numbers. So 3 minus 0.9 going to give us a 2.1. So again, a 2.1 is definitely above 2. It's going to be an ionic bond here. And really, once again, I didn't really need the numbers because sodium's a metal, chlorine's a non-metal, so it's definitely going to be ionic in this case. And the reason why I said, again, sometimes the 2 is just an arbitrary number. If you took something like, I don't know, let's see what we got going on here. Do something like, maybe something like lithium bromide there. If you take the difference between lithium and bromine, bromine is looks like 2.8 and lithium is 1. That's a 1.8 difference, obviously less than 2, right? But it's still an ionic compound, so the 2 is sort of a general number for ionic sort of bonding. And again, just the metal, non-metal. If you take a look at fluorine here, F2, fluorine is 4 and fluorine is 4. So obviously here, if I take a difference in electronegativity, that is 4 minus 4, which is 0. And that obviously falls between the 0 and the 0.4, and that's definitely a non-polar bond. And I'll be honest with you, sometimes people, when you do have a difference in electronegativity of exactly 0, some people will call it a pure covalent bond. And you'll sometimes hear pure covalent bond. And that's like as perfect equal sharing of electrons as you could have, really like a difference of 0. And that would technically be what is sometimes referred to as a pure covalent bond. A pure covalent bond is still a nonpolar bond, equal sharing of electrons. So it kind of does mean the same thing in a sense, but it just indicates that it is like perfectly equal sharing. Remember that our cutoff for nonpolar goes from 0 to 0.4. So technically speaking, at like 0.4, for example, we are not perfectly equal sharing of electrons, but it's not so unequal sharing that it's considered polar. It's still sort of in the, okay, it's close enough to being equal sharing, but it's not perfectly equal sharing like you would have, like we could do here with a difference of 0 in terms of its electronegativity value. If we take a look at HF here, H is 2.1. F is 4. So again, we could calculate the difference in electronegativity. 4 minus 2.1. It's a lot of math at this point, but that's 1.9 here. And 1.9 falls in the category of kind of 0.5 to less than 2. And that's going to be polar in this case. And that's going to be a polar covalent bond. By the way, again, if I were to draw my arrow, we should be pointing it towards the fluorine, obviously, in this case. That is more electronegative in this particular case. We could see that at 1.9, hydrogen is like just barely hanging on to that rope, as 2 is our cutoff for ionic almost, right? Ish, in that ballpark. So it is super unequal sharing of electrons. And there are various degrees of unequal sharing, you know, there's a little unequal sharing. And then something like this where it's definitely a lot of unequal sharing sort of happening in this situation. Any questions on that there? Let me see here. So why don't you try some here? Why don't you do these here? Use the table. Obviously, the table or the values would be provided for electronegativity if you need it. So why don't you calculate the difference in electronegativity for the following and determine is it ionic, polar, or nonpolar? All right, so let's say we have a bond between, we'll do carbon and hydrogen, a bond between carbon and nitrogen, a bond between sulfur and oxygen. Let's see, let's do nitrogen and chlorine, and let's do potassium and chlorine. All right, so take a moment for each of those. Determine its a difference in electronegativity values based on the table, and also is it ionic, polar, or nonpolar? And for any polar one, 0.5. Hydrogen is 2.1. So again, if we do the difference in electronegativity, 2.5 minus 2.1, going to give us a 0.4. And 0.4 is the upper limit for nonpolar. And the reason for that is pretty much all organic compounds are carbons and hydrogen based. And that bond is nonpolar. A lot of organic compounds are nonpolar. And that's why the limit there is 0.4. So 0.4 is still considered nonpolar. Once again, this is not perfectly equal sharing of electrons, but enough to be considered still equal sharing of electrons in this case. If we take a look here at carbon, which is 2.5, and our nitrogen there, which is 3. So we take a difference in electronegativity. That's going to be 3 minus 2.5. That's going to give us a 0.5. And 0.5 is above 0.4. And this is going to be a polar bond. With the arrow should be drawn towards the nitrogen, as it is more electronegative in this case. That would mean in this bond, the nitrogen should be more negatively charged, right? More partially negative. And the carbon in this case should be more partially positively charged. Any questions on that? Taking a look at our next one, which is sulfur and oxygen. So sulfur is 2.5. And oxygen there is 3.5. So our difference in electronegativity here, 3.5 minus 2.5, going to give us a 1. Once again, here, 1 is definitely above 0.4, less than 2. So this is going to be a polar bond as well. With once again, it is the oxygen here is going to be more electronegative, and we should draw the arrow pointing to the oxygen, which will be more negatively charged or partially negatively charged in this bond. Any question on those there? We take our potassium and chlorine. That is definitely going to be ionic. I don't even really need it because that's a metal and a non-metal. In this case, it might work out okay. Let's see. So potassium is 0.8 and chlorine is 3. So our difference in electronegativity, 3 minus 0.8, 2.2. That is definitely above 2. And again, I don't really need the numbers because, again, metal and a non-metal in this situation. Any questions on that one there? Now, taking a look at nitrogen and chlorine. Nitrogen is 3, and chlorine is 3, if I'm not mistaken. So difference in electronegativity here looks like a big 0, I think. And that definitely is going to be a nonpolar bond. This would also be a pure covalent bond. And does bring up a good point that definitely if you have two atoms that are the same in a bond, it's definitely going to be nonpolar because they're the same. They're going to share the electrons equally. But it is possible to have two different elements within a bond that will also share the electrons equally. The reason for this is what's sometimes referred to as like a diagonal rule. If you look at the location of nitrogen and chlorine, they are diagonal from each other, not right below each other, but down and over one. One is further up and one is further to the right. They cancel out their differences. There's a few sort of diagonal relationships that you see, carbon and sulfur and so forth. And again, there are some sort of diagonal, not right below, but kind of one over diagonal from each other. So it is definitely possible, as you can see here, to end up with two different elements within a bond that is still going to share the electrons actually equally. Any questions on that? Now, strictly speaking, for the most part, we use electronegativity values like this to help us understand what is referred to as bond polarity. So there's two different types of polarity we'll see in this chapter. One is bond polarity, which is what we're talking about here. And within bond polarity, all we are simply asking is between these two atoms, how are they going to actually share electrons? Has nothing to do with the entire molecule as a whole or anything like that. It is just simply between these two atoms. We could use the difference in electronegativity to help us decide, will we get a polar bond or a nonpolar bond? There is something known as molecular polarity, which takes the entire molecule into account. And as a whole, all the bonds present, the entire whole molecule, is the molecule sharing electrons equally or unequally. And that is what is known as molecular polarity. And again, we'll talk about that later on in this chapter. The only place where those two actually cross over and are exactly the same is actually, like, for example, HF. In HF, that bond is a polar bond based on electronegativity difference. That was the one we got 1.9 when we did it. And if you look at HF, it has only one bond total, right? And because that one bond is polar, the molecule will be polar as well. If you look at F2 or even H2, both of those bonds give you a difference in electronegativity of 0. And they both only have one bond between the two H's, between the two F's. And because that one bond is nonpolar, the molecule will also be nonpolar. So when we have diatomic molecules like HF, F2, H2, because they only have one bond, if the bond is polar, the molecule will be polar, and they will not share electrons overall equally. And if the bond is nonpolar, the molecule will be nonpolar. That's the only place where bond polarity and molecular polarity basically cross over and is exactly the same. When you have more than two atoms involved, especially with molecular polarity, there's a lot more things to consider that we'll talk about in this chapter. Any questions on that there? Now, the question is, do you need these numbers and to use these numbers all the time? The answer is no, you don't. You can make probably, in a lot of cases, a pretty good estimate based on the general trend in electronegativity as to whether or not you'll have a polar bond or not. Again, increasing as you go up and to the right, decreasing as you go down. For example, if I'm comparing two atoms in the same row, like we did right here with our friend carbon and nitrogen, they're in the same row. And nitrogen is further to the right, which means nitrogen should be more electronegative than the guy that came to his left, and that should give you a polar bond. So without even the numbers, because they are in the same row, if you have a bond between two things in the same row that's a nonmetal and sharing electrons, most likely that's going to be a polar bond, and you don't have to actually need the numbers to do that. Same thing if you're comparing somebody in a group up and down on the periodic table, like we did with sulfur and oxygen. Sulfur and oxygen is in the same group, and oxygen is further up on the periodic table. And that would tell me that oxygen is more electronegative than sulfur. And that should also give you a polar bond. So you absolutely probably don't even need the numbers if you're comparing something that's in the same row or something that's in the same group. Just by the fact that they're in the same row or same group, they will have some differences in electronegativity that usually will lead you to a polar bond, and again, in the case of obviously sharing electrons. Any questions on that? So as we saw there, atoms with widely different electronegativity values tend to give away its electrons and form ionic bonds. And that is again why when we put something on the left-hand side of the periodic table, something on the right-hand side, just that big difference in electronegativity is going to cause that transfer of electrons to occur. Again, when we get everybody in the same region, like nonmetal and nonmetal action, because they both want the electrons, we're just going to end up sharing electrons. And that is, again, why we get these general rules of what happens, metal, nonmetal, ionic, two nonmetals sharing of electrons and covalent. Now, as I mentioned before, there is no sharp distinction for that kind of two cutoff. And again, as we saw there, there's some examples where, you can have an ionic compound that has less than two difference. Now, we don't usually use it all that much, too much, but in terms of polar, nonpolar, ionic, sometimes people will use what is sometimes referred to as percent ionic character to describe a bond. Not too much used a lot by people these days. But if you have an ionic bond, then it is definitely 100% an ionic character. If you have a pure covalent bond, a nonpolar bond, you're going to have more like a 0% ionic character is going to be more of a covalent bond and have a 0% ionic character. So sometimes people will classify sort of bonds by percent ionic character. And again, it's sort of the same idea there. 100% there, 0% there, and somewhere in the middle there is your polar percentage along the way. Now that we've talked about how electrons are shared in covalent bonding and what types of bonds that we do end up with covalent bonding, let's talk about the steps that you should follow when you draw Lewis structures for covalent bonds. So earlier in this chapter, we showed sort of Lewis dot symbols to show ionic bonding, where we have the transfer of electrons and we get things with charges. Here we're going to talk about the steps you should follow when you are drawing Lewis structures for covalent compounds where they're sharing electrons. If you follow these steps, it should really lead you, in most cases, to a pretty good Lewis structure. Will be the best one in 100% of the cases? No, but 99% of the time, you'll get a pretty good structure that's going to come out of it. Now, the first thing you want to think about is, how is the thing kind of put together? And to help you sort of decide how things are put together, there are some rules that we want to follow when we draw Lewis structures. And those rules are this. Basically, the least electronegative atom, the one that is the least electronegative, should be in the center. And probably in a lot of cases, everything else is attached to the guy in the middle. And the guy in the middle should usually be the least electronegative. That means that hydrogen should not be in the middle because, again, hydrogen cannot have more than two electrons, so never ever in the middle of hydrogen. And because fluorine is the most electronegative, You cannot put fluorine in the middle usually, and it should usually be on the outside. Probably the most important thing when you go to draw your Lewis structure is this. You want to count up the total number of valence electrons there are in your picture. And that number is really important because when you're done drawing your picture, you got to be exactly on that number. You can't have any more or any less electrons. You got to hit that number on the nose. Again, the number of valence electrons equals the group number. Also, if you are drawing a Lewis structure for an ion, like a polyatomic ion, which we'll talk about in the next chapter as well, and it does have a charge, you do have to adjust the total number of electrons for its charge. So a polyatomic anion would be negatively charged, and you would have to add however many the negative charge is. For a cation, we subtract the positive, not negative, my positive charge from the total. So if you have an ion that you are drawing, you want to add the negative charge. So if something has a -2 charge, you need to add it to your total. And if something has like a +1 charge, you need to subtract an electron. Otherwise, you'll end up with too little or too many electrons for your picture. The next thing that you want to do is, after you got kind of an idea of how it should be put together, you know how many electrons you need to use. The next step that you want to do is, from the center atom to each of the outside atoms, you basically want to draw one single bond. So if this was my outside atoms and that was my center atom, the first thing I would do is draw one single covalent bond. Not double, not triple, a single bond. Remember that each of those lines represent 2 electrons. So in my picture here, I've now used 6 electrons, 2 for each line. I'm going to subtract that from my total number of valence electrons, and I should have some electrons left over at this point. All those electrons you still have left over should go on the outside atom until each outside atom has the magic number of 8, except for hydrogen that's on the outside. No dots, yes, so it should only have 2. You're going to go around and basically fill up all the outside atoms with dots until they all have 8. At that point, you're going to run out of outside atoms. And one of 2 things will happen at this point. Either you will run out of electrons, or you will still have electrons you need to put on there. So if you still have electrons you need to put on your picture at this point, and you filled up everybody on the outside, you should go to the center. And the center atom should be put on as dots as well. Let's come back here. So you should then go and kind of put some on as dots in the center atom as well. At this point, if you get to the center atom and you're putting some dots on there, you should be out of electrons at some point, at that point when you do that. And the last thing that you want to do is, after you do all this, you then want to go through each atom in the picture, and you want to make sure that it has met the octet rule. Everybody should have 8, except for, again, hydrogen should only have 2. It is at that point that if somebody does not have 8, you're going to try to fix it by making a double bond. And you want to exhaust all your double bond options. And if the double bond fixes it, you're done. If the double bond does not fix it, and you have no other double bond possibility, then you want to go to a triple bond and make a triple bond. So as I mentioned earlier, you want to start single bonds. You want to then fix things with double bonds if necessary. If not necessary, don't double bond. If the double bonds doesn't fix the problem, then you want to go to triple bonds. And that usually leads you to a pretty good picture when it's all said and done. A couple of things you want to think about when you're drawing these. First off, you should think about them a little bit different than how we did ionic bonding, that these electrons that we calculate in step 2 does not belong to anybody. So sometimes people, when they go to draw these things, do it in piecework. They go like, okay, well, you know, nitrogen's got 5, oxygen's got 6. They got to kind of move over this way and try to figure out where each of the electrons go. The better way to think about it that will get you the right picture and not a picture where you have too many bonds, not enough bonds, too many electrons, not enough electrons, is to think about the electrons as belonging to not necessarily anybody, but what we want to do is like evenly kind of distribute all those electrons as best we can to everybody, rather than like this guy's got 5, I got to get him to 8, and this guy's got 6, I got to get him to 8 by 2, and that's a much better way of doing it. Any questions on that? All right, so let's take a look at one here together and see the approach. So here, NF3, the first thing really you want to do is, or the first thing really I do is the total number of valence electrons. So I'm going to go to the periodic table. Remember that the valence electrons equals the group number. So nitrogen here, and we have 3 fluorines. So each nitrogen is 5 from group number 5. There are 3 fluorines, each one's 7 from group 7. That means 21 and 5. 26 valence electrons is the magic number for my picture in this case. I have to hit exactly on that number. I can't have any more, any less. When I look at nitrogen and fluorine in terms of elements, I know fluorine is more electronegative than nitrogen. And remember that the least electronegative should go in the center. So the least electronegative atom should go in the center. By the way, just a common rule of thumb, not 100% always right, but if you have one element and 3 of some other, usually the 1 is in the middle a lot of times and everybody else is attached to it. So a logical arrangement for this would be like nitrogen in the middle, fluorine on the sides. You can think about it as having 4 sides. Now in this particular case, I did put the fluorine on the bottom. If you wanted to, you could put the fluorine up on top. It doesn't really matter. You could do the top or bottom. Now, the next thing I'm going to do, once I have the logical arrangement, is this. Just a single bond. I'm going to use lines. If you want to use dots, you can, but I'm just going to use lines and do one line to everybody. And again, at this point, each line represents 2 electrons. So that is 2, 4, and 6. If I subtract that off from my total, I'm down to 20 electrons I need to put on my picture at this point. Once again, these 20 electrons do not go on as individual electrons. They go on as pairs of dots. Yeah, so pairs of electrons, basically. And we're going to go 2, 4, 6, 8, 10, 12, 14, 16, and 18 at this point. If I just add up all the electrons I've put on there, by the way, I went 2, 4, 6 because there's already 2 there, right? So that's 8. 2, 4, 6, 8. 2, 4, 6, 8. So again, I have successfully got 8 around everybody on the outside. And that's a total of 24 electrons I have now totally placed on this thing. That means I still have 2 electrons to go. So I'm down to 24. So 2 electrons to go. Those 2 will now go to the center atom also as pairs of electrons. And now I have now placed all 26 electrons on my picture. First off, any questions on that there? Lastly, I do want to make sure everybody's still good in terms of the octet rules. So going in blue, 2, 4, 6, 8 for that one. 2, 4, 6, 8 for that one. 2, 4, 6, 8. And for the nitrogen, 2, 4, 6, and 8. Everybody has 8 electrons. A lot of highlighting, but everybody has 8 electrons. And we have used only 26 electrons in our picture. And this would be the proper Lewis structure here for NF3. Any questions on that there? All right, so why don't you try one here? Why don't you do... Why don't you do this one? Let's try nitrate, NO3 minus. So this whole thing has a -1 charge. Give it a try and see what you come up with, and then we'll talk about it here in just a second. Here we could start with our number of valence electrons. So we got 5 for our nitrogen, which is group number 5. There are 3 oxygens. Each is group number 6, right, for our oxygens. And that's going to give us 18. Now, this thing does have a -1 charge. And again, negative means that it has gained electrons. So here we do want to add 1 electron to our total because it does have a negative charge. Otherwise, again, you're going to be off. I will say it is possible, but not in this class. So it is possible to have an odd number of electrons, but for this class, everything should come out nice and kind of paired up. But maybe when you get to 1A, you'll talk about some of those actual examples. All right, now that we have that, again, if we look at the periodic table, we want to think about our arrangement. We probably want to add it up first too. 18, 19, and 5 is 24 valence electrons. So again, 24 valence electrons is what our picture should have. If we take a look at the periodic table, here's nitrogen, here's oxygen, here's fluorine, by the way. And we can see that oxygen is further to the right on the periodic table, which means it's more electronegative. And that would tell me that probably nitrogen should be in the middle. Here, the 3 oxygens most likely are going to be attached to the nitrogen in sort of our logical arrangement. So once again here, we can arrange it with 3 oxygens around our nitrogen. And once again, even though I did put the oxygen there to the top, you could put it to the bottom if you want to go that way as well. We're going to follow our normal rule here, which is it's just a single bond from the center to the outside. And we're going to do 1, 2, and 3. That once again is going to use 6 electrons, 2 for each. So if we just subtract out off, that's 18 we'll go with. So we got 18 electrons still to go. Again, that's going to go on the outside here. So 2, 4, 6, and that one is filled. 8, 10, and 12, that one is now filled, that oxygen. 14, 16, and 18, that one is now filled, that oxygen as well. That's also 18 more electrons, which means I'm down to zilch left. At this point, I have now placed up there all 24 of my electrons that I'm supposed to do in my picture. Is everybody good in this case? Everybody is not good. Everybody is good in terms of oxygen in this case. All the oxygens are good. It has 2, 4, 6, and 8. They're all the same. But the nitrogen here in the middle has 2, 4, and only 6 electrons. So it is the nitrogen here in the middle that's actually short. So this is a situation where we have now placed all of our electrons, and not everybody has met the octet rule. Remember, the whole purpose of bonding, right, is for everybody basically to get to that 8 electrons and being really stable. This is not a good situation for nitrogen because it did not get there, right, to what it needs to. So this is a case where we do have to fix it and get everybody to 8. Can I just, if I wanted to, just like slap a couple of electrons right about there? Can I do that? Clearly I could do that, but I should not do that because now how many total electrons do I have? Not 24, I got 26. Too many electrons. So we can't fix it by just adding some extra electrons. Remember, the purpose of the first number is that's the number we have to have. We can't have any more or any less. So this is the point where we want to kind of fix it by trying to make a double bond. And in this particular case, if you look at all the oxygens, all 3 of them, there are basically identical oxygens. So you could actually make the double bond to any of those oxygens you want. You could do it to the top one. You could do it to the guy on the left. You could do it to the guy on the right. They're all what are referred to as being equivalent to each other. So you can make a double bond to any of them. So if I wanted to make a double bond to fix the situation, and let's just say I want to double bond the top guy, can I just draw the double bond line in this case? The answer is no, because now you also now have 26 electrons. And by the way, the oxygen on top now has 2, 4, 6, 8, 10 electrons. Doesn't sound like the octet rule with 10 electrons, right? So that's not good. So when we go to kind of fix it by making a double bond, and by the way, also when you go to make a triple bond, if necessary, what we're actually doing is we're going to take a pair of electrons from that atom that we want to double bond with, and we're going to bring them in to make the double bond. So for example, I would take perhaps the pair of electrons up here, and I'm going to bring those guys in to make that double bond, and that's where the double bond is going to come from. The result of that is I will now end up with a double bonded oxygen up on top, and I will still have my 3 or my 2 oxygens that have bonds, electrons around them. And we could put a little box around it, a bracket with a charge, since it's an ion, and that's typically what you do. Put little brackets around things that have charges and put the charge on the outside. Now, did I fix the problem? Let's see. Well, if I take a look at the oxygen over here, 2, 4, 6, 8, so it's good. I look at an oxygen on the left, 2, 4, 6, 8, it's good. Double bonded oxygen, 2, 4, 6, and 8, so it's good. And now my nitrogen, which was the problem before, 2, 4, 6, and 8. Everybody has 8 electrons. If you count up the total number of electrons, before I highlighted everything, you have 24 total electrons. So we have the right number of electrons. Everybody has gotten to the octet rule. Everybody's super happy in that case. Yes. Any questions on that? Now, we were talking about a second ago that you really could have, if you wanted to, double bonded to any of the oxygens. And if you double bonded to the right-hand oxygen instead of the top one, you would end up with a picture that looks something like this. This guy would still be single bonded, and we just double bonded over here. Also still giving us 24 electrons, and everybody still has 8. You could have also, again, double bonded there to the oxygen on the left, and you would end up with a picture that looks something like this. Single bonds on the right and top, and double bonded over here. And again, we would end up with 24 electrons, and everybody has 8. These are all actually related to each other. These little arrows heading in both directions, and all these structures, these are what are referred to as resonance structures. Even though they don't want to talk too much about that anymore in this class, but this resonance structure is a good thing to know, I suppose. And basically resonance structures happens just like this, where you have basically more than one option as to where you can make that double bond. And you could draw an equivalent Lewis structure, no matter which one you draw. They're all 3 of these structures here are all equivalent to each other. They're all basically the same. And the reason you're able to do that is because in reality, when we bring those electrons in, those electrons that make up the double bond are sometimes referred to as being delocalized, which means they don't belong necessarily to one atom versus the other. They're actually moving around. So at any given point in time, those double bond electrons you use to make the double bond could be over here at this oxygen. They could be up there on top to that oxygen. They could be over there on the right-hand side. So no one Lewis structure by itself, because you have that option, those double bond electrons moving, really adequately describes what's going on. So you could draw multiple Lewis structures to sort of describe what happened. The true picture is somewhere in between all 3 of those. Some type of hybrid of what's in there is truly what's happening in this case. Any questions on that there? Now, for our purposes in this class, you don't have to draw all 3 resonance structures or anything like that. If you drew any one of those 3 structures, that's bracketed, you'd be good for this question. Yeah. Any questions on that? When you get to 1A, they'll definitely want you to draw some resonance structures and stuff like that. All right, let's do a few more examples here. Drawing. Let me just make up some stuff here to draw. Why don't you draw the Lewis structures for the following? Why don't you draw a Lewis structure for SH2, SO2, CO2. I feel like I'm doing a lot of twos there. Just do NH4 plus. Let's do N2 as well. Why not? That'll work for now. All right, so take some moments here and draw up some proper Lewis structures for each of these. See how you do. And we'll add one more. ClO3 minus. All right. See how you're doing. So we'll just start with the first one. Why not? Seems like a good one. Let's go this way. All right, so we're gonna go SH2. So once again here, I'm gonna start with really the total number of valence electrons in the entire compound. So sulfur, I believe, is group 6 there. And again, we have 2 hydrogens. Each hydrogen is going to be 1. So that is 8 valence electrons in this case. Obviously here, logical arrangement would be sulfur in the middle, hydrogen connected. As we've talked about a number of times, we do not put hydrogen in the middle, right? So just a logical sort of arrangement will look something like this. Again, we're going to follow our normal rules here, which is we're going to make a single bond from the center to the outside. That again has used up 4 electrons, as each line represents 2 electrons. I have 4 more to go. Can I put dots on hydrogen? That is the right answer. Don't put dots on hydrogen. So because hydrogen's on the outside, it has 1 bond. It's good. It's got 2, right? So no more. So now, just like normal, once everything on the outside's filled, we're going to go to the center, and we're going to put the center as pairs of dots. So 2 and 4. We have now placed all 8 electrons. Our hydrogen on the right here has 2, so it's good. Our hydrogen on the left has 2, so it is good. Our sulfur in the middle has 2, 4, 6, and 8 electrons, so it is good. And now we have our correct picture here for SH2. Get rid of all my check marks here. And it looks something like that. Any questions on that one there? All right, taking a look at the next one, a little SO2 action here. So same idea here, SO2, sulfur is group 6. There are 2 oxygens, each also group 6. So we got sulfur there and oxygen. That's 12, and 6 is 18 valence electrons in our picture. Once again, if we look at the periodic table, sulfur and oxygen are in the same group, and oxygen is further up, which means it's more electronegative, and that means sulfur here should be in the middle. So we're going to go sulfur in the middle. I'm going to do some oxygens on either side. We're going to do our single bond from the center to the outside. And once again, that is 2 and 4 electrons. If I subtract 4 off of here, I got 14 more to go. Again, we're going to go on the outside ones until everybody on the outside has 8 electrons, and these are going to be pairs of electrons or dots. So 2, 4, 6, that is filled. 8, 10, 12, that is filled. At this particular moment in time, we have placed 16 electrons up there. And I have 2 electrons still to go, basically from my original 18. That then goes to the center atom, and there should also be a pair of dots there. And now I have placed all 18 of my electrons. So here again, we want to make sure everybody's good in terms of the octet rule. Oxygen has 2, 4, 6, and 8. The oxygen on the other side is the same. The sulfur in the middle has 2, 4, and only 6. So in this particular case, our sulfur is not in good shape, as it does not meet the octet rule. So now that we've placed all of our electrons, something has not met the octet rule. We're ready to do our fixing procedure, which is now we're going to go to a double bond. Once again, in this situation, both oxygens are exactly the same. So you can make the double bond at either oxygen as you like. Remember, as we talked about, when we make the double bond, we're actually going to take a pair of electrons and move them in to make the double bond. Again, we're not going to add any or just add a double bond. And if you do that, you will end up with a picture where you now have a double bonded oxygen on the right, still a single bonded oxygen on the left. And now if we take a look at it, we have 2, 4, 6, 8 for that oxygen, 2, 4, 6, 8 for that oxygen, and for the sulfur, 2, 4, 6, and 8. So again, Everybody now has 8 valence electrons around them. They've all met the octet rule. And you will also see that it is not a double bond on this one, which is a very common error that people make when they draw this. It's not 2 double bonds. Those 2 dots need to be non-bonding electrons on the central atom. And again, if you go through the procedure like we did, you will place them as dots and not a very common misdrawn Lewis structure where you double bond both sides in this case. So you want to make sure you don't do that. By the way, this is another resonance structure. Again, if you double bonded the oxygen on the other end, you would end up with a picture that looks like this, which is perfectly fine as well. So again, you could draw either one. Any questions on that one there? Okay, so we got that down. We got that down. A little CO2 action here. So let's get over there. So CO2. Again, counting up our valence electrons, carbon is 4. And there are 2 oxygens, each are 6. So carbon and oxygen. That is 16 valence electrons. Once again, carbon and oxygen are in the same row on the periodic table. Oxygen is further to the right, which means it's more electronegative. So remember, the least electronegative should go in the center in most cases. And that's going to be carbon in this case. And again, I'm just going to do some oxygens around it, or to the sides. And we're going to do our single bond. So we're going to do 1 bond, 2 bonds. That is 4 electrons at this point. That's going to leave us 12 to go on the outside. 2, 4, 6, 8, 10, and 12. At this point, taking a look at it, oxygens are okay. Carbon is well short. It has only 4 electrons at this point, 2 from each of the single bonds. So here we want to try to fix it. So your choice, left or right. I'm going to double bond left in this case and bring the electrons in to do so. That's going to give me a double bonded oxygen on the left and a single bonded oxygen on the right. Did it actually fix the problem for carbon? It did not. It got better. He now has got 6 electrons, closer to 8, but he does not have 8. So now what we want to think about is, what should we do next? Well, you do want to usually, in most cases, exhaust all your double bond possibilities. And in this particular case, we have that other oxygen on the other side that we could also double bond. And you would want to probably do that before you jump to triple bond. Yeah. So again, you kind of want to exhaust all your double bond options before you jump to triple bond. So I'm going to do the same thing. I'm going to bring a pair of electrons in to make that second double bond. And we will end up with now a double bond on both sides. And now everybody, including the carbon in the middle, has 8 electrons. And we still only have 16 total electrons in our picture. Again, you would not want to triple bond this side for reasons we don't get to in this class, things like formal charge and stuff like that. It's the double bonded oxygen on both sides is actually a better structure than, say, the triple bonded one. So like I said, if you kind of follow those rules, single bond first, double bonds, and then triple bonds, not in 100% of the time, but in most cases, it will lead you to, a lot of times, the better structure or good structure. Yes, sir. You can actually triple bond it, but what is known as formal charge wise, it doesn't create a good structure for that compound. It creates something with a bad formal charge sort of situation or charge situation on those things. And the double bonded here on both sides is much better. All right, so we got CO2 done there. Now we have ammonia, which is NH4 plus. So we'll do that one. I'll flip a page here, I think. So we have NH4 plus, N2, and ClO3 minus. All right, so looking at NH4 plus here, nitrogen is 5. There are 4 hydrogens, each at 1, which is 4. This plus charge means that it has lost electrons. So in this particular case, we actually want to subtract 1 because of the positive charge. Again, we don't want to add here because it's not a negative charge. Negative we would add, positive charge we want to subtract. That's going to give us 9 minus 1, which is 8 valence electrons. Once again, we do know that hydrogen will not go in the center, so that does leave nitrogen as your only option in this case. And we're going to do a single bond to everybody. And that is 2, 4, 6, 8 electrons, which means I'm out of electrons at this point. So now we just need to make sure if everybody's okay. Each hydrogen only has 2, which is good. Nitrogen in the middle has 8, which is also good. So just to finish it up, because it does have a charge, brackets and the charge on the outside, and we're good to go on that one. Any questions on that? Last, or 2 seconds to last, nitrogen. Valence electrons 2 times 5, which is 10. Now, even though there's only 2 atoms here, you could actually follow the same steps and same procedure, and it will get you hopefully to the right answer. In this case, there really is no center atom, so you could just kind of put them kind of facing each other is a good way to go. And once again, you can follow the same deal, which is I'm going to connect with a single bond, which is 2 electrons. That gives me the 8 left. You could choose whichever one you want and start putting your electrons on. So 2, 4, 6, and 8. At this point, I have now put all 10 of my electrons on. The nitrogen on the right is in good shape. It's got 8 electrons, but if we look at the nitrogen on the left, it has only 4 electrons. So this nitrogen over here, not so good since it only has 4 electrons. So we're going to try to fix it by double bonding first. So just like we did previously, we're going to take a pair of electrons and bring it in. And when we do that, we will end up with something that looks like this. And in this situation, it did not fix it. It got better. Our nitrogen on the right has 8. Nitrogen on the left now has 6. 2, 4, and 6 at this point. Now there is no other option for double bonds here, since there's only one bond to begin with. So now we move to triple bond, and we do the triple bond the same way. We're going to take a pair of electrons and move it in to make our triple bond, and we will end up with a triple bonded nitrogen. And now we have something that has 10 total electrons. Each nitrogen now has 8 electrons, and that's again how nitrogen gets to a triple bond. Again, it's got to keep kind of going until everybody gets to that octet rule. Any questions on that one there? All right, last one on tap here, ClO3 minus. So Cl is chlorine, which is 7. There are 3 oxygens, which are each 6. And again, we have a -1 charge, which means it has gained electrons. So we do want to add 1 for the -1 charge. And that's going to give us 18, 19, a lot, 26 valence electrons in this case. In this case, we're going to go chlorine in the middle, as oxygen is a little higher up, even though it's a little bit over to the left. So we're going to go chlorine in the middle, oxygen around, and once again, usually if you have one element and multiples of the other, usually the one element kind of ends up in the middle most of the time. We're going to do a single bond to each. So 1, 2, and 3, that is 6 electrons, leaving us 20 more to go on the outside in pairs. So 2, 4, 6, 8, 10, 12, 14, 16, and 18. Gets us 2 left over. We have now placed on this picture 24 electrons. We have 2 more to go. That is now going to go to our center atom, which is chlorine. And now we're just going to check to make sure everybody's good. And each oxygen has 2, 4, 6, and 8. They're all the same oxygens. Chlorine, 2, 4, 6, and 8. So everybody is good. The chlorine has 8. All the oxygens have 8. Once again, it does have a negative charge, so perhaps just clean it up a little bit with a little bracket and a charge on the outside there. And you'll end up with something like that. Yeah. And that. Sorry, that. Hopefully you can see that you do want to make sure you just follow those steps. It should really lead you to a pretty good structure. You don't want to do any type of piecework that, again, may get you the wrong structure. It can. They do actually have a charge. They have a formal charge. Each of those oxygens are actually -1 charged. So there are a couple of things, but in this case, for our purposes here in this class, you would single bond everything. You wouldn't want to double bond. For our purposes here, it would go over the octet rule, right? If you start double bonding things for the chlorine, even though chlorine can go over the octet rule, but in this class, everything will obey the octet rule. Yes. Yeah, so in this case, again, single bonded here, gets the job done, and that's where you should lay it up. Other questions? All right, we were laid up there for today.